I'm not muted, but maybe I needed this microphone on. You can now. Okay. Thank you. Good to know. So the main focus of the next two sections is to be able to take a function that you probably were never expected to graph by hand without a calculator. But now that we know something about a derivative, you should be able to come up with a reasonable sketch for any kind of a graph now using the derivative. And we'll see the first and second derivative. The book usually professors kind of take it slowly, like they've only talked about the first derivative for one lecture, and then they talk about the second derivative and how that applies to the graph. Thank you. But I've always thought the best, let's just get into it. Let's graph a function in its entirety. We'll talk about how the first and second derivative are useful for that, because that's the end goal anyhow. So, okay. So we'll start with I think the easiest ones that work for this are just polynomials. Most of you probably know what a general x cubed graph looks like. What do they kind of look like in general? People going like, yeah, like little things like this, right? And not only with cubic functions, but all polynomials, this is kind of important. No matter how I sketch it, I'm just going to graph a random polynomial. They might go like this, have some wiggles in them, and then finish this way. Other polynomials might go like this and go this way. The point I wanted to make was that they always, at their ends, either in this direction, my polynomial is going off to positive infinity, and to the left, it's going down to negative infinity. So at their ends, all polynomials will go to plus or minus infinity. Okay, thanks. Again, it doesn't have to look like this. You know, they can both be going to positive infinity, but there's no like horizontal asymptotes or anything involved with polynomials. Okay. Now, if I was going to graph it, I think easy points to add to your graph are x-intercepts. When your graph crosses the x-axis, y is equal to 0. So we can just set f of x equal to 0. Do some factoring. It's like I can pull out an x squared. And if 0 equals x squared times x minus 3, then I have two x-intercepts, one at 0, one at 3. So what I'm going to do, slide this up here. Did I do that too fast? This is where I'm going to graph my function right here. So I know my cubic equation is going to hit the x-axis at 0, and let's say this is 3 right here, 3, 0. Okay. The next thing, if I was graphing a polynomial, let's go back to my fake graph right here. If I wanted to know what this graph looked like, if I wanted to reconstruct it from the equation, I would want to know what this point was, this point was, this point was, and this point was, because that's where it's kind of turning around, right? And then here's the idea, here's the difference. If you look at a polynomial like this in its entirety, would it be correct to say I'm going to choose this point? Is that the absolute max? Is that the highest the function ever gets to? Obviously not, right? It goes up forever in this direction. How about, either one of these? Is this an absolute min? No, right? That goes down low to infinity, negative infinity in this direction. How many people agree that if for many, many polynomials, there would not be an absolute max or an absolute min, right? There isn't any. That's because we don't have a closed interval. Now there could be, just think about a parabola, right? A parabola goes off in both directions, but there is a minimum, right, at the vertex, and that is an absolute minimum, isn't it? Doesn't go any lower. So there's no guarantee. But what we do call these, we call these either local, this could be called a local maximum, I guess both of these. Other common name for local means like nearby, right? You're local. So the way I think of that is if you're near that point right here, if your x value is near that, then that is a maximum. If you're nearby, also called a relative maximum. That means relative to points around it. That is a high point. Thank you. And then same thing over here. These 2 points could be called local minimums. I'll just use local. And I would want to know those. And how do I find those? Well, just a little bit like we were talking about on Wednesday, those would be places, at least for this graph, where the derivative equals 0, right? My derivative is equal to 0, which that's one of the ways to find a critical point, right? A critical number. So anytime you're looking for local extrema, we're going to take our derivative. You still see the equation. I'll slide it back up here. There it is. Easy derivative, 3x squared minus 6x, and I'm going to set it equal to 0. I'll say find critical points. Here I can factor out a 3x. And so I have two critical numbers here, either x is 0 or x is 2. Okay. Oh, now the way it works is these are critical numbers. These are places where the derivative is 0, which means the graph is flat at these points. But you know, in both cases, it could be a max or a min, right? In both cases. So we have to now distinguish, you know, is one of these a max, one a min, or vice versa, or are they both min, something like that. Now, there's a few different techniques out there for how to proceed and determine which one's a max, which one's a min. I don't care for our book's method. And I'd be willing to bet with 3 or 4 different professors teaching 17A, they all have kind of slightly different methods. How many people are interested in learning what I think is the most efficient and easiest way to do it? Okay, even if it's different, and your professors are fine with that, even if it's a little different. Okay, so here's what I do, and I have a feeling James probably would do this too. Once you get your critical numbers, we're just going to draw a number line. And above the number line, we're going to collect information about the derivative. And below the number line, we're going to interpret that as, what does that mean about our function? And so what we're going to do is pick test numbers. This might sound like if you were doing domain problems earlier in the quarter, sometimes you have to do like a number line. So we're going to pick test numbers. I need a number less than 0, maybe something like -2, something between 0 and 2, like 1, something bigger than 2, maybe 5. So these are just test numbers. And what I'm going to use these for is to test them into, that's why I put the numbers up here. I'm plugging these into the derivative, okay? And I'm interested in whether the derivative is positive or negative. So let's just work from right to left here. If x is 5, now you can plug it in here if you want to, but I think it's easier to plug in here. If x is 5, 3 times 5 is positive, 5 minus 2 is positive, a positive times a positive gives me a positive. If x is 1, this is going to be positive, but 1 minus 2 is now negative. A positive times a negative gives me a negative. And if x was -2, this will be negative, this will be negative. So you have a negative times a negative, which is back to being a positive. Now, what does this mean then? If my derivative is positive, let's go back to my little fictitious graph here. Maybe I'll use a different color. I got too much red here. When the derivative is positive, it means the slope is positive, right? So everywhere like right here, my derivative is a positive slope. What does that tell me about the function if my slope is positive? Will it be increasing or decreasing?
It's like me.
Yeah, it's definitely going up, right? If you got a positive slope from left to right. And vice versa, if your slope is negative, your derivative is negative, it means your graph is going down. So what I do, I'm a visual person here. Underneath here, if my derivative is positive, it tells me my function is going up. So I just draw a little arrow kind of going up like this. Negative means it's going down. And then positive means back to up.
Today and yesterday.
And this is what my graph is looking like. So this is kind of giving me an insight to my graph.
Right now,
It goes up until it gets to 0, and then it goes down. So kind of visualize that. If you had to decide whether 0 corresponded to a local min, what would you be inclined to say?
This is black.
It goes up and then down. up and then down. That's a max, huh?
Don't
That's a
want
max.
the professor.
So what we know is you're gonna have I use sometimes abbreviate local max
Get a really bad professor.
at 0 something.
I get a
And then
really
if you
bad
go
professor.
from down to up, you're gonna be passing through a local min at 2 something.
Yeah, that's it.
Now with this technique, everything has a purpose here. I put my points here to find the y values. I'm going to be plugging these x values. Notice I'm below. I'm plugging these back into I want the derivative. I'm plugging back into here.
What?
Remember my original function I think was x cubed minus 6x squared. So if I plug in, well, we already had that. That was one of my intercepts, 0, 0. But if I plug in 2, I get 8 minus 24. I think that's negative 16. So let's add that to our graph. We already have 0, 0. Let's just call this 2, negative 16. And then it goes back to what I was saying before. We know it's increasing. So sometimes I know the homework, they ask you for the intervals on where it's increasing. And that's pretty easy. When you just follow the arrows, it's increasing on the interval from negative infinity until I get to 0, and also from 2 to infinity. Oh, thank you. So that changes this. Where did I get the 6x squared? I don't know. Yeah, maybe my function was x cubed minus 3x squared. So that's actually, what should this point be? 8 minus, it's only negative 4, isn't it? Okay. 2, negative 4, good catch. And if you had to write the intervals where it's decreasing, you know it's going down between 0 and 2, not including, right? Because at those points, it's not really, it's actually flat, huh? The graph is flat there. It's not really increasing or decreasing. But when we say increasing from x equals negative infinity to 0, we know it's a polynomial. So it must be coming, if it was increasing, it must be coming from negative infinity, coming from down here. We know this is a maximum. Then it's going to come down, hit this minimum at 2, negative 4. And then, oh, I'm going to maybe miss my point. I'll just move my dot right there. And then pass through our x-intercept at 3, 0. Okay. So with the first derivative and finding some intercepts, you got a pretty good idea of what the graph looks like. But we take it one step further to get a full accurate graph. One of the things we're interested in is, notice how the graph is curving down here. Looks like a frown. And then this part's kind of curving upward like that. And so we're interested in when a graph is curving down versus curving up. When a graph is curving down like this, we call this concave down. So I'll just write over it. This part of the graph right here is concave down. I always just say, it looks like that's the part of the graph that's frowning at you, huh? And part of the graph is smiling at you right here. This part is concave up. And if you kind of estimate, where does the graph transition from a frown to a smile? I'm going to say maybe about right there. It's starting to go from a frown to a smile. That point where it transitions in the concavity is what we call it. That point has some special features oftentimes when we apply it. Anybody know what that's called? It's called an inflection point, yeah. And so we want to find that in many cases. You'll be asked to find it. Now, how do we find that? Let me ask you this, so that it makes sense. What we were just talking about up here is that if my derivative is greater than 0, in other words, positive, right? Who's increasing? If my derivative is positive, we know that f of x is increasing, huh? If f prime of x is greater than 0, then f of x is increasing. Fill in the blank for me then. What do you think it would mean if f double prime of x was greater than 0? Then who should be increasing? How many people see the logic in saying that would be f prime of x is increasing, right? Because this is the derivative of that. If this is greater than 0, that's increasing. So if this is the derivative of that, if this is greater than 0, this should be increasing. So the question is then, what does a graph look like where your derivative is increasing? What does that look like? So let me show you on this other page here. Okay. Take a graph like this, something that looks obviously like a smile. And let's think about, I don't have any axes or anything, but suppose I were to measure the derivative at various points. Remember, the derivative is the slope of your tangent line. So right here, I'm just going to put f prime, I'm not going to put x. How many people agree that's a negative slope? So would it seem reasonable? Let's just say, what if I said the derivative here was -4? That seems reasonable, huh? The negative slope. Tell me about right here. What's the derivative there? If this slope's -4, would you say this is -5? How many people agree that's less steep? So give me a number. Doesn't matter. You can't be wrong. If this one's -4, what could this one be? You said it wouldn't be -5, right? Because it's not more steep. It has to be less steep. -2, maybe that's -2, huh? What's the slope right here? That's 0 because it's horizontal. How about right here? Maybe +2, maybe right here, that's back to +4. From left to right, what's happening to these numbers? -4, -2, 0, 2, 4. -4, -2, 0, 2, 4. How many people agree the derivatives are increasing? So what does it look like when the derivative is increasing? It looks like this. It's concave up, huh? It's concave up. So what we learn from this is anytime a graph is looking like this, what we could expect to be true is my second derivative should be greater than 0. Right, to be concave up. I usually do that, CC up. And as you might expect, if you have a graph that looks like this, which is concave down, then your second derivative is going to be less than 0. Very easy to remember. You know how I remember this? When the graph looks like this, the second derivative is, what's another way of saying greater than or 0? Greater than 0. Positive, right? Second derivative is positive. What do positive people do? But sometimes you can't see behind their mask. How many people agree positive people smile a lot, right? And negative people frown, huh? So if the second derivative is negative, it's going to look like a frown. So pretty easy to remember that. It could be a nice compliment to somebody, right? You say, hey, you're looking very concave up today. You having a good day? All right, that's great. Smiling. Okay, so all of that was just a little background. So how we're going to find the concavity, I need to keep this paper handy. We want to locate this point and we want to identify where the graph is concave up and concave down. We're going to go to our second derivative. Now remember our first derivative, I'll put it up here, was, that's right, it was 3x squared minus 6x. So my second derivative (6x minus 6). That's pretty easy. That's equal to 0 when x is 1. Now, we don't call that a critical point. We save that for the first derivative, okay? So nothing with the second derivative we call a critical number. But here's what we're going to do. The same exact process. When you find where your second derivative is equal to 0, we're going to put it on a number line. Above the number line, though, we're going to collect information about the second derivative, and below the number line, we're going to interpret that as what is that doing to the graph. Let me just slide this up, don't I? So just like the last one, I need to pick a couple test numbers. So something less than 0, something less than 1. How about 0? Something bigger than 1. I don't know, 17, huh? I sometimes joke like that because people are like, why'd you pick that one? Just any number, right? Any number bigger. Okay, if x is 0, my second derivative, that's why I'm plugging it in, is going to come out to be negative. That's easy to see. And if x is 17, 6 times 17 minus 6 is clearly positive. Now here's what I mean. What does that mean about the graph? If the graph second derivative is negative, it means my graph is frowning at you, huh? It's frowning. And if it's positive, it's smiling. And this place where it transitions, the place where it transitions from a frown to a smile, that's what we call an inflection point. So we could say we have an inflection point. I use IP at 1 something. How do I find the y value? Plug 1 into who? Because I'm down below here, huh? Everything has a meaning. So I'm going to plug it into my original equation, which was x cubed minus 3x squared. So that's going to be -2. And then I can come back here and update my graph here, right? I could say, I'll put this up here temporarily. I now know this inflection point is at 1, -2. So what happens is you learn these tools and they start with polynomials, hopefully, because those are the easiest. And then we start to make the functions more complicated. You do these with rational functions. You do them with log functions, exponential functions, trig functions. But polynomials are a little bit simpler. So let's do this as a practice one here. So on your papers, if you're tuning in online, let's see, at least get through your x-intercepts and your local extrema, and then see if you can draw your graph. I find 90% of the time, just by knowing the first derivative, where it's increasing and decreasing, you can get a pretty good idea of the graph, even without looking at the concavity. Okay, I'm just getting caught up here. Got intercepts of 0 and 4. And got my derivative. By the way, some of you, if you took pre-calc, might remember about like x-intercepts that kind of go through or bounce off the x-axis. What do they call them? Kiss or cross. Sometimes they teach that. So that you might notice some of those things are still true here. But anyhow, first derivative, I got 0 and 3 as my critical numbers. So now I'll pick some test numbers. -1, 1, whoops, x equals 10. -1, if I plug it in here, squaring it, that's going to be positive. 1 minus 3 is negative, though. So that means this is going to be negative. So that means my function's decreasing. When x is 1, that's going to be, hey, notice this is always going to be positive, isn't it? We can guarantee that because I'm squaring that. So I really just have to worry about this. 1 minus 3 is still negative. So this is still decreasing. X equals 10, positive. 10 minus 3 is positive, plus going up. So what we know for sure is that 3, the graph went down and then up. So we know this is a local minimum. Yeah, down and then up from left to right. But at 0, right, in order to be a min or a max, it has to change. It has to go down and then up, or up and then down. So this is really nothing in terms of extrema. Do remember, though, that when x is 0 and x is equal to 3, my derivative is equal to 0. So if you could even do this, you could say, well, that gets flat there, doesn't it? I know I have a horizontal tangent line, same thing here. So then that might help when you're graphing this. Oh, I need, so this point was 0, 0. I need a point for this, 3, comma. Did anybody plug it in? It's just, yeah, I think I can squeeze it in right there. This was my function in factored form. So if I plug in 3 there, that's 27. 3 minus 4 is -1. So I'm pretty sure this is -27. Okay, so then we're going to sketch this. So we know the graph to the left is decreasing. So the polynomial means it must be coming from way out here up in positive infinity area to be decreasing. But we have to think about if it's going to get flat as it gets to the origin and then decrease again, what must happen is it must look like this. To get flat like that, it's going to have to curve like a parabola. But then what happens after that is it's going to dip down to hit this point, which I should probably, there we go. Just get rid of those. That's my point now. And then it's going to increase forever. Horizontal tangent line right there. This is, I sometimes think of these polynomials. They're kind of like if you've ridden a roller coaster. Ever ridden a roller coaster where you like go down like this and instead of going up, it kind of drops down again and you kind of lose your stomach? Have you ever felt that before? It's kind of, yeah. Okay, so that would be our graph. Now we're going to look at the concavity too, and I think it's worthwhile to kind of look at this if we're pretty sure that's what the graph looks like. Show me on your fingers in here, type in the chat at home, how many inflection points do you anticipate finding if that's the graph? How many places do you see where it transitions from a smile to a frown or vice versa? Remember, it doesn't have to be a full smile. Be part of a smile and then transition to a frown. I'm seeing some 1s and 2s and some, it's okay to not know. I'm looking in the chat. Nobody. Okay. Yeah, I was thinking at minimum, see right here, the graph is looking like a smile, huh? Concave up. But then at this point right here, if it's going to go back down, do you see how it has to switch to concave down here? So I'm anticipating, in fact, I'm anticipating it's going to happen right there, huh? Right at the origin, inflection point, most likely, right? But then it's concave down. But do you see, in order to finish this part, it's going to have to transition back to a smile. So there's probably going to be another one right here. I'm thinking 2 is probably a minimum. We might get another one. Maybe there's something else over there. But it'll come out when we do the second derivative. So if you haven't already started, take your second derivative and see if you can locate your inflection points. My kids don't like to ride roller coasters with me anymore because they say I embarrass them. So like, last time we were riding a roller coaster like this, everybody usually goes, yay, and I'm going, yay, inflection point. And my kids are like, Dad, why does everything have to be math with it? Yeah.
So wait, why is the x at 4, 0 again?
Oh, that was our X-intercept.
Why isn't it at 3?
Our X-intercept we found by factoring out x cubed from the beginning, not from the derivative. And that's an optional step, but if you're going to graph a function, isn't it nice to have a couple points so you know that it goes through, right? And those are just usually easy points. I always tell students, if you get a graph and it looks like the X-intercepts are going to be really impossible to find, just don't worry about it, go on to the derivative, but it is nice to have those points if you can. All right, so my second derivative. Yeah, working from here, I'm going to get 12x squared minus 24x, factor out of 12x. I get 2 not critical numbers, but places where the second derivative is equal to 0. Some test numbers. X is -1, that's negative, negative. Whoops, I shouldn't circle it. Okay, that's right. Negative times a negative makes it positive, so that means the graph is concave up from negative infinity to 0. That totally matches up, right? From negative infinity to 0, it's concave up. So you can almost, that's one nice thing, if you draw the graph with the first derivative, you can almost, if you're pretty sure you got it right, you can almost predict what this is going to be. If x is 1, that's positive. 1 minus 2 is negative, so this should be negative here, concave down. That's what we saw in between there. And if x is 5, then they're both going to be positive. So it's concave up. So as predicted, we have 2 inflection points. And 2 f of 2. I'll just think like that. Okay, I wanted to show you one more because the 2 I showed you were polynomials, and they're the easiest kind of graphing ones, believe it or not. And maybe because of that, sometimes professors think, well, that's too easy to put down on a test. Polynomials are a piece of cake, so I'm going to make something a little more challenging. So let me show you one that is not a polynomial. And I'm sure next week, any questions on this? Oh, 3, yeah, okay, I was at to see the inflection points, yeah. I'm sure next week, James will show you more graphing with even different kinds of functions. But here is one, and this is not a polynomial because there's that 2/3 power. Polynomials have to be whole number powers. So the graph's going to look a little bit different than a polynomial. So x minus 3x to the 2/3. I'm still going to try to find my x-intercepts here. And we found to find the x-intercepts, it was helpful to factor. So if I have x to the first and x to the 2/3, I'm actually going to take out x to the 2/3 because that's the smallest power. If I take out x to the 2/3 from x to the, that's just 1, what power will be left? 1/3. I'm going to have x to the 1/3 minus 3. So if 0 equals x to the 2/3, certainly if x is 0, that's going to be one place. But the other one's going to come when I set this equal to 0. If I set that equal to 0, that's x to the 1/3 equals 3. You can change that to a cube root if you want. Or just cube both sides. That means my other x-intercept's going to be at 27. Let's just call this 27. I keep doing that, and then I end up changing my dots. All right, let's take your derivative, which is going to be kind of ugly. You're going to get 1. Fortunately, 2/3 times 3 is just minus 2x. Subtract 1 from that, though, gives me to the negative 1/3 power, and I have to find out where this is equal to 0. Well, this is the same as 1 minus 2 over x to the 1/3. And what I recommend doing on these problems for critical numbers, I know mathematically it's easy enough to just move that over, do some cross multiplying. But think ahead to the number line. You know, when we put plus or minus, we mean bigger than 0, less than 0, right? So we kind of want to keep our derivative equal to 0 if we can. There are times I violate that if I really get stuck with the algebra, but if you can, try to keep it equal to 0. So instead of moving that over, what I'm going to do instead is create a fraction, multiply top and bottom by x to the 1/3, get a common denominator. So that my derivative, 1 times x to the 1/3, I get x to the 1/3 minus 2, all divided by x to the 1/3. I remember asking this last time. When I have a fraction's equal to 0 when which part is 0? Top. So I know this derivative is going to equal 0 when x to the 1/3 minus 2 is equal to 0, which means x to the 1/3 equals 2. Cube both sides again. When x is 8. So that is certainly a critical number, but who remembers from last time, what else qualifies as a critical number? Not only where the derivative is equal to 0, but where it's undefined. And a fraction, this fraction would be undefined when x is 0. Yep. So both of those count as critical numbers in this one. That's one thing that's a little bit different. I'm going to do my number line right here. Pick some test numbers here. I was thinking too, it pays, you'll see when you get into more complicated functions, you know, I've been picking random numbers, but sometimes you're going to think about where you're going to plug that into. We're all okay with something to the 1/3 means the cube root, right? Means the cube root. So I want to pick numbers that have nice cube roots. -1 is fine. 1 is fine. But, you know, normally like a number bigger than 8, I probably wouldn't pick 9 because I don't know what the cube root of 9 is. What's the next number besides 8 that has a nice cube root? Right, 3 cubed is 27. So me personally, I would pick 27. Not for being silly, but for knowing that that's going to be easier to plug in. Cube root of -1 is -1, right? -1 minus 2. So when x is -1, my numerator is going to be negative. And the cube root of -1 is negative as well. This will be negative. A negative over a negative makes this positive. If x is positive 1, cube root of 1 is 1 minus 2 is still negative, but the cube root of positive 1 is a positive number. Negative over a positive is negative. And then if x is 27, that'll be 3 minus 2 is positive 1. And of course, that'll be 3, so that's positive. So we do get increasing, decreasing, increasing, which means we have a local max at 0 something and a local min at 8 something. Well, 0 was one of our intercepts, so we've got that one. Let's try plugging in 8. Scratch paper. You know what? I'll deal with the concavity later. Remember, my function was x minus 3x to the 2/3. So if I were to plug in 8, I'd get 8 minus 3 times 8 to the 2/3. On the screen, there we are. 8 to the 2/3. Cube root of 8 is 2. 2 squared is 4. That's going to be minus 12. 8 minus 12 gives me negative 4. Okay, let's add these points. Now, you got to be careful on this one. It's not a polynomial. Okay, here's why. We have this 1, 0, 0 is a max, right? And we have it increasing and then decreasing. How can I do this without? I should have brought a pencil. What I want to do is write and then erase, but I don't have a pencil. Oh, here we go. Here we go. I'll just use a substitute paper. So don't write this down. You're at home. Don't write this down. Okay. We have it increasing, decreasing, and then increasing. Why can the graph not look like this? This point was 8, negative 4, and this was 0, 0. Why? Who knows why it cannot? Oh, you gotta see it first of all. Why can't it be this? Not this. Exactly. Right? If we draw it like this, it makes it look like the slope of the tangent line was equal to 0 at 0, huh? But if you go back to how we got 0 as a critical number, it was from the derivative being undefined, not equaling 0, right? What's one situation you've seen where a derivative can be undefined at a point? I can think of 2 off the top of my head. What kind of a line has an undefined slope? Do they still do this? Because there was a few algebra books when I was teaching high school that drove me nuts. Horizontal line has a slope of 0, right? Rise over run. And there was a few of the older algebra books, they would say if you had a vertical line, they would say no slope. That always drove me nuts. I know why they said it, but it always drove me nuts because I had this vision. I was like, okay, suppose you were out hiking with your friends and your friend said, hey, go hike down that trail. It has no slope. What are they really telling you to do? Jump off a cliff. Vertical, right? I don't like that term, no slope, to mean a vertical. I prefer to say the slope is undefined, right? So if you have a derivative that's undefined, what could happen is there could be a vertical tangent there. Your graph could literally go vertically for a second. Or, and I think we saw this last time, what's another situation where the derivative can be undefined? Okay, there's a third one. But along with piecewise, meaning, I mean, if it was defined, if it was continuous still, if they meet up with different slopes, you get a corner, right? Or a cusp, a corner, a cusp. Remember that I think I even used x to the 2/3 last time. Remember I showed you that's how I draw my birds. It has a little cusp. So if you think about it, the only way that this could go up and then down and have the derivative be undefined is if it came in in a sharp point like this, and then came down. Because we need to show that our derivative is undefined at 0. Cusp. Can you see why a professor would like to choose one like this to make sure you're really paying attention, right, to what the derivative means, right? Not just, draw a polynomial there. So watch out for that. Now, I'm kind of out of time here, but if I miss that, if for some reason I drew it like this instead, you know how I'm going to catch myself? If this was the correct graph, how many inflection points would I have? You see there's one maybe about right here, changing from concave down to concave up, down to a smile. So if this was the right graph, I would expect to get an inflection point. If this is the right graph, how many inflection points do I get? How many times does it change concavity? You're shaking your heads, huh? There wouldn't be any, huh? This graph is always concave up everywhere, isn't it? It's always smiling. It's a very happy graph. Okay. So if you want to try it, I'm out of time here, but if you take your second derivative, you should be able to see that it's always positive. There's no place the second derivative is ever negative, which means that's the right graph. So. Okay, well, I got 3 graphs in. How's everybody online there? Good, okay. I think James will be back on Monday. And again, I don't know if this gets recorded and where it goes, but I can maybe try to message James and see if he'll answer. But yes, thank you, everyone. You all signed in. James told me you all know how to sign in. Okay.